I'm going to briefly describe a pressure temperature diagram for a single component, in this case looking at water. And first thing to point out is that notice the y-axis pressure is plotted on a log scale. We're covering a fairly broad range of pressure. Next is that this diagram is really a projection of a 3D surface. Namely, when I move to a different point on the diagram, volume can change significantly. So we divide it into three regions: solid, liquid, and vapor. And then we have phase lines. So this line describes phase equilibrium between liquid and vapor. If you specify a temperature, there's only one pressure where vapor and liquid will coexist in equilibrium. Important point, this critical point, and so the liquid vapor phase line ends at the critical point, whereas the solid liquid line continues off this scale, and it may bifurcate and form several phases of solid, but it does not have a corresponding endpoint. Well, this means above this critical temperature and pressure, because this corresponds to critical pressure and a critical temperature, we have what's referred to as a supercritical fluid. This also means there's not a sharp distinction between liquid, supercritical fluid, and vapor, but it's a continuum. I'm going to look at a simulation to describe a little better the behavior of this system. So let's look at the phase behavior on this diagram. As I add heat to the system, and start out with liquid, once I hit this phase line and I continue to add heat, notice the temperature doesn't change, so I'm adding heat, and what's happening is I'm making more vapor and less liquid. The same type of behavior happens if we started with a solid and we added heat, and we're at low pressure now, and we'll go directly to a vapor. So we have solid vapor equilibrium, and at constant temperature we're now subliming the solid, so this is sublimation going from solid to vapor. Well, we have the corresponding transition going from solid to liquid. So at higher pressures, namely at pressures above the triple point, as I add heat, I'll get to the phase line, and now solid converts to liquid at constant temperature and constant pressure. So I'm showing here in this insert a very expanded x-axis. Notice we're only covering 0.16 degrees on this plot. So you can see that this line that slopes to the left means that if I increase the pressure on a solid, I'm going to convert that solid to a liquid for water. Water is relatively unique in this behavior in that raising the pressure on a solid forms a liquid. So we've seen that for water, as we increase the pressure, and it's a little more difficult to see on this particular plot, but remember we're going at constant temperature, we go from a solid to a liquid. However, water is unusual, and for most materials the behavior is such, and I'm going to exaggerate, the line looks like this. This means if I have a liquid and I increase the pressure at constant temperature, I will convert it to a solid. So for example, for carbon dioxide, that's a behavior that we will see. But otherwise, the behavior of carbon dioxide is very similar in terms of phase diagram, though the scale would be different.